Hi everyone, my name is Timo Walter and I'm a committer in the Apache Flink software project. In these videos, I would like to share knowledge about Apache Flink, stream processing, and general software engineering topics. This video is about Flink SQL or Flink SQL, and I would quickly like to give you an introduction. Before I start, let me briefly also talk about what is actually SQL. And I know I know that all of you know SQL, right? So I actually don't have to explain what is SQL. Like everybody understands statements like select hello world, creating values, performing a where condition or filter condition, performing a join on two tables based on a key, right? Like SQL is a very popular language, and yeah, it is human readable, and yeah, like it is present in many systems and databases. And of course, even if the examples get more sophisticated, you still know what's going on, right? You like everybody or almost everybody has written a create table statement in the past. You are well familiar with the type system, and you also know what an insert into means and what a join condition or a where clause means. So we don't have to talk about SQL. We can directly jump into Flink SQL. So what is Flink SQL? So first of all, this is the API stack that you see in Apache Flink. The SQL API coupled with the table API is the highest layer in the Apache Flink code base. So basically, the runtime is far away. There are other components in the middle. So the SQL API sits on top of an optimizer and planner. The planner then talks to a low-level stream operator API, which I will not cover in this talk. And then the operator API will talk to a data flow runtime on which our SQL queries are executed. So great. We all know that Apache Flink is a stream processor. Flink is famous for working with streams. So the next question that I would like to answer is, how do I actually work with streams in Flink SQL? And the answer to that is actually you don't work with streams. You, as a SQL user, you work with tables. We usually call them dynamic tables because they have some dynamic component, but still, from a conceptual level, they are still regular tables as you know them from databases. But the way how we deal with these tables is a concept very similar to materialized view maintenance known from databases. So, but let me start from scratch. As you know it from databases, you usually create a table, maybe some source table, and you create another table maybe for storing some results. And in the middle, you just perform a SQL statement. You submit a SQL statement. If the input table would be bounded, so would end at some point, also the insert into would end at some point. But Flink usually gets unbounded input tables, so infinite data comes into Flink. And this is why the insert into in Flink is usually an endless operation that consumes from the input table and writes to the output table. So this is where Flink slightly behaves differently from regular SQL, that Flink is able to digest constantly changing input tables. But still, the question often comes, is Flink SQL a database? Because it looks like a database, right? And the answer is usually no. Flink is not a database. You bring your own data. Flink is not a storage system. You can connect your storage systems to Flink. So Flink focuses on the processing part and is a very good data processor. It kind of acts as a hub between the different tables, between the different external systems. So now let me also talk a little bit about how can we now work with streams if we actually work with tables. And this is a principle, you can also look it up online, that often pops up, the so-called stream table duality. So what does stream table duality mean? You can at any point in time convert a stream into a table or a table back into a stream. So even if a table is constantly changing, you can derive a changelog out of this constantly changing table. And if you would apply this changelog again on a fresh table, you would actually see exactly the same table again. So you can go back and forth without changing the results. And here I have brought an example for that. So on the left side, we have transactions. On the right side, we have the result table, revenue. And what we are doing here is a very simple SQL statement where we read from the transactions, we group by name, and per name, we are summing the transaction amount. So let's take a concrete look here. Let's assume there is a record coming in. A row comes in, Alice with amount 56. And this we can also represent in the changelog. So that would be an insertion, right? So we are inserting something into the table. The changelog represents that as well. And this insertion would be entered into the engine, and the engine, Flink SQL, would then emit another changelog, in this case just the same record. And if you would apply this changelog now to a different table or key value store, you would also see the results. And let's assume there is another row coming in, Bob this time, no problem. Bob is inserted, the engine will compute the sum and emit Bob in the output. This was easy because everything was insert only. But usually there's more updates happening in your query. So let's assume there is another Alice row coming in, and this is where we actually have to refresh our sum, because even though the input is an insertion, because we are using a sum, the sum that we emitted before, the 56, is not valid anymore. So the first thing that we have to do is the engine has to send out an update before to delete the row that was previously stored in the table. And then we are inserting a fresh record with the updated sum. But as you can see, still, if you just look at the left, the right side, and in the middle, this is also what a typical database system would create. So again, an applied changelog just becomes a real materialized table. Okay, so now we have seen Flink SQL, and also we have also looked at some SQL queries already. And not everybody likes SQL. If you think about it, SQL is super old. Why should we use this 40-year-old legacy? Why is SQL still a thing? Why should you maybe think about using SQL in your organization? So first of all, SQL is declarative at its core. So it's kind of a very old YAML file, right? Or yeah, it's just a pure declarative API or endpoint. So in SQL, you usually don't work with files. You don't work with any kind of threading or any kind of low-level primitives. You don't see network connections. You don't perform resource management. Usually the SQL engine cares about all these things for you. Then SQL is also a human language, right? It's not a very mathematical language. So almost everybody can read a SQL statement. And even though this almost human language has a lot of keywords, these keywords have a ton of meaning and a ton of abstraction behind it. Let's just look at this very simple example here, select and select distinct. Just the distinct keyword will deduplicate records for you, but like under the hood, this is a big amount of work that the engine has to do for you, right? Like it's a completely different code path and yeah, more stages under the hood, but you can just enter distinct and the engine will do the rest for you. And if you're using a keyword at the wrong location, or if like the types don't match, then it also performs eager validation for you. And that is super useful, right? Like you don't want to wait an hour in order to get a validation error. No, you want to get this upfront before you start processing your data. So all these kinds of properties here make SQL as recent as other programming languages. But still, not everything in SQL is imperative. So I think in general, there is a very nice trade-off between some stuff is declarative and some stuff is imperative. Because we also have, like in Flink SQL, for example, we have show, describe, drop, and alter, which allow you to change the state of a database. And of course, there are things like SQL scripts that really allow you to define a program that is imperatively executed from top to bottom to create tables, alter tables, insert data or copy data from table A to table B, and so on. So yeah, like SQL unifies both the declarative world and the imperative world using its human language or almost human language. And then there is this whole universe of optimization. So first of all, SQL knows about everything that's going on, like what you want to join or what you want to union. It knows all the fields. It can break objects into pieces. It can move around parts of the pipeline, for example, moving the filter closer to a source. It can also detect that some parts are maybe not necessary, so it can project out fields for you. It can remove unnecessary parts of the pipeline, or if it sees that like some parts are done multiple times. For example, here in this union all, the engine can detect, wait a second, we are reading 2 times from users, and we can just read from users once and then perform the filtering by address is not null or address is an empty string. Right? So we can derive common parts and process only once and read only once from a table. And for engineers, there is also a lot of stuff that we can do if we know the statement or the query well. So we, for example, can work on binary data. We can pass pointers instead of large memory segments or large pieces. We can perform lazy deserialization if we are in a distributed setting. So like we can work and implement a lot of efficiency improvements under the hood without changing the original query. And for theorists, there is of course also this relational model or like relational algebra. It's a well-researched field. There are tons of papers out there how you can improve a join or an aggregation and so on, and like how you perform cost-based optimization. So all of that is done for you under the hood in the SQL engine and planner. And while researching for this presentation, I was actually also researching how old is SQL actually. I said 40 years old, and I think the standard is 40 years old. But actually, if you look at at old papers, SQL is actually even older than that. It's 50 years old. Like the first paper that was written by Cott 1970, has actually a quite interesting an abstract, and I want to just quickly read this abstract out loud here, because I think it clearly states what SQL tries to achieve here. It says future users of large data banks must be protected from having to know how the data is organized in the machine, the internal representation. A prompting service which supplies such information is not a satisfactory solution. Activities of users at terminals and most application programs should remain unaffected when the internal representation of data is changed, and even when some aspects of the external representation are changed. Changes in data representation will often be needed as a result of changes in query, update, and report traffic and natural growth in the types of stored information. So you can see even 50 years ago, people tried to still solve problems or try to solve problems back then that we are still trying to solve today. And if you just look at the SQL standard, so the SQL standard is ISO 9075, you see that the SQL standard is actually massive legacy. It's the result of very long negotiations, endless discussions in the standard committee, involving so many different people, industry leaders, generations of engineers and data experts, right? So SQL standard is actually the result of hard work, and we are actually far away from being complete, and you can see that in the standard releases, right? SQL is not a dead standard. Until today, like you can see, the last standard was released in 2023. And this is just a rough outline of what's going on in the standard. Especially the part 2 is interesting. The part 2 is the foundation, and this foundation part has actually, until today, it has 1,700 pages, right? So it's a massive guide, a massive information for all developers and implementers, users out there, that people have spent a lot of thought into a language that basically everybody can use. So now we talked a little bit about the past, right? We talked about the SQL standard, but now let's talk about the state of SQL today, and especially the state of Flink SQL today. So the SQL standard gives us a very good foundation. We have a well-defined type system, right? Like you're familiar with types like varchar or timestamp. We have a catalog integration. Everything is properly schematized. You can just do a select from T, and the system immediately knows what T is, what the data types of T are, and how it can read from T. And you have schema awareness at any point in time, at any stage. So like here, this is a typical example that I show usually is, do you understand what this query does? You maybe don't understand it, but the engine still knows what to do, right? So it knows that this one is a catalog, this one is a database, and this one is a table. And this might be a field, and then you might access the field of this field. And and then maybe you just want to call the mathematical pi function here. So like the system has schema awareness from source to sink, and knows exactly what's going on. And of course, you don't have to include libraries. Most of the most commonly used operations are already built in. So extracting year from a timestamp, uppercasing, or some standard deviation. All of these built-in operators, functions are present in a SQL database. And of course, you have this giant ecosystem. SQL editors, JDBC interfaces, CDC connectors, and a lot of other tools such as DBT and so on. So like the Flink like Flink SQL is not just Flink SQL, it's an ecosystem. It's a Flink SQL ecosystem. So the foundation is actually very good that, that Flink SQL can be used to power the instant world, to really solve real-time use cases and perform real-time analytics. But we're not done yet, and that is a very important thing here to mention. There is more, right? Like first of all, our goals as Flink SQL people are that, we don't want to introduce new keywords. We don't want to come up with our own new Flink SQL language. We want to power the instant world with existing standards. We want to perform stream processing and event-driven applications with existing standards. And luckily, there is not only the foundation standard, but there are also the so-called guidances for the use of the database language SQL standards. So this is ISO 19075. And I just want to quickly dive into two of those extensions or additional appendixes to the SQL standard. For example, part 5 is about row pattern recognition. And part 6 is for supporting and processing JSON. So you can really see that also this part is evolving and new pieces are added as the data processing world evolves. For Flink and Flink SQL, our goal here is that we want to streamify mature infrastructure, right? So we want to attach to the CDC log of an old database. We want to get real-time insights out of Kafka, out of databases or other external systems, and trace changes and perform change data capture. And I will definitely also publish another video just on the topic of change data capture, but this is just an introduction here. So stay tuned for more videos. So now let's really take a look at some parts of the SQL standard. For example, row pattern recognition. Let's assume we have some stock data with a symbol, some timestamp, a price, and some tags. And the question now is, find the longest period of time for which the average price of a ticker did not go below a certain threshold. And how should I express that in SQL? And there was a new clause introduced, the so-called matRecognize clause. And this clause allows you to define a pattern that is similar to regular expressions. And you can define what these patterns mean. So what is A? A is defined as this, and what is B? B is defined if it's not A. And then you can search for these patterns in the data. And if you find these patterns, you can also perform aggregations and perform measurements on the found pattern. So it is possible to do complex event processing with SQL, and also this is built in Flink SQL. This would be the result in that case. And JSON is everywhere. People want to use JSON in almost every API. And of course, also the SQL standard has evolved and supports JSON. And here you can see some Flink SQL, like how you can process JSON, right? Like we have special built-in functions and keywords for checking the validity, whether this is valid JSON. We have aggregation functions that, for example, allow you to create an array out of some input table. You can extract information using JSON query, or you can also construct JSON using JSON object. And there is way more in Flink SQL, so this was just the tip of the iceberg. Of course, Flink SQL allows you to do stream stream processing. So stream processing also means you have to deal with time, and you might want to create some windows to cut your stream into pieces. That is also possible. So we have tumbling windows, session windows, and other kinds of windows. And there are some specialized operations, for example, time version joins, which allow you to view a constantly changing table at a certain amount of time. So for example, if you have an orders table and a currency rates table, it is possible to join an order with a current state of a currency rates table at the point in time when the order was placed. So these are just a couple of more examples, but actually I would suggest actually to publish a video on each of these examples in the future. So in general, stay tuned. I will publish more videos, and I hope you roughly know now what is Flink SQL and what you can do with Flink SQL. But I will definitely show you more examples and how you can make use of Flink SQL in your organization. Thank you for watching, and see you next time.